Welcome to our lesson on the Schmidt process. This powerful technique allows us to convert a set of linearly independent vectors into an orthonormal basis. Let's break down what this means and why it's important. First, let's clarify our goal. We start with a set of linearly independent vectors v underscore 1, v underscore 2, up to v underscore k in r to the power of n. We want to transform these into a set of orthonormal vectors u underscore 1, u underscore 2, up to u underscore k that satisfy three key properties. Now, let's understand the basic orthogonalization step. Suppose we've already constructed orthonormal vectors u underscore 1 through u underscore j1. To form u underscore j, we need to make it orthogonal to all previous vectors. First, we project v underscore j onto each previous u underscore I using the formula. Proj underscore u underscore v underscore j equals v underscore j that u underscore I times u underscore f. Next, we subtract all these projections from v underscore j to get a vector w underscore j that's orthogonal to all the previous u vectors. W underscore j equals v underscore j minus the sum from I equals 1 to j minus 1 of v underscore j dot u underscore I times u underscore I. Finally, we normalize w underscore j to get our unit vector u underscore j by dividing w underscore j by its length. Let's put all the steps together into the complete Schmidt process. For the first vector, there are no previous vectors to subtract, so w underscore 1 is just v underscore 1. We then normalize it to get u underscore 1. For each subsequent vector j from 2 up to k, we first compute w underscore j by subtracting all projections onto previous orthonormal vectors, and then normalize to get u underscore j. Let's work through a simple example in our squared to see the Schmidt process in action. We'll start with two linearly independent vectors, v underscore 1 equals 2, 1, and v underscore 2 equals 1, 3. We'll visualize these in the Cartesian plane. Let's apply the Schmidt process. Step 1 is to normalize v underscore 1. We compute the length of v underscore 1 as the square root of 2 squared plus 1 squared, which is the square root of 5. Therefore, u underscore 1 equals v underscore 1 divided by its length, which is 1 over square root of 5 times 2, 1. Step 2 is to orthogonalize v underscore 2 against u underscore 1. First, we calculate the projection of v underscore 2 onto u underscore 1. This is v underscore 2 dot u underscore 1, which is 1 times 2 plus 3 times 1, all divided by square root of 5. This equals 5 divided by square root of 5, which simplifies to square root of 5. Then we multiply by u underscore 1. Next, we subtract this projection from v underscore 2 to get w underscore 2. This is v underscore 2 minus square root of 5 times u underscore 1, which equals 1, 3 minus 2, 1, giving us dash 1, 2. Step 3 is to normalize w underscore 2 to get u underscore 2. We compute the length of w underscore 2 as the square root of negative 1 squared plus 2 squared, which is also the square root of 5. Therefore, u underscore 2 equals 1 over square root of 5 times dash 1, 2. Now let's verify that u underscore 1 and u underscore 2 form an orthonormal basis. First, they should be orthogonal, meaning their dot product is 0. U underscore 1 dot u underscore 2 equals 2 times negative 1 plus 1 times 2, all divided by 5. This is negative 2 plus 2 over 5, which equals 0. Second, each vector should have unit length. We already computed that both u underscore 1 and u underscore 2 have length 1. So our final orthonormal basis is u underscore 1 equals 1 over square root of 5 times 2, 1, and u underscore 2 equals 1 over square root of 5 times dash 1, 2. The Schmidt process works because at each step, we carefully remove the components along the directions we've already selected. This guarantees orthogonality. Then by normalizing each vector, we ensure they all have unit length. Importantly, at each step j, the span of the first j orthonormal vectors u underscore 1 through u underscore j is exactly the same as the span of the original vectors v underscore 1 through v underscore j. The Schmidt process is a powerful tool in linear algebra with applications in many areas, including numerical methods, computer graphics, quantum mechanics, and statistics. By transforming arbitrary, linearly independent vectors into an orthonormal basis, it allows us to work with more structured and well-behaved vector spaces. Thank you for watching this step-by-step explanation of the Gram-Schmidt process.